All right. Good morning, good afternoon, good evening, everyone. What's that?
I would clear my screen, or how, or are people just going to follow along?
After the introduction, after the introduction, you'll be able to share the screen.
Yeah.
Perfect.
So I'm gonna, Kiri, you're a co-host now, yeah?
Yeah.
Okay, cool. So we still have some people trickling in, but I think it wouldn't hurt if I just start the introduction now. Welcome, everyone. Welcome. Thank you for joining us back. I know it's been a bit of a dense week for the first week, but the second week will be less dense. So let's get started. One second. Yeah, and Brad, if you can keep letting people in, meanwhile, that would be wonderful. There we go. Cool. Perfect. Okay, welcome back, everyone. And this is the wrong slide. Hold on. One second.
While you are searching for the, you are fixing the slides or opening it up, just letting you know that the tutorial today is at 2 p.m. EDT. And also, if some of you have, it's difficult to find the time zone, I'll share a link to find exactly, to transfer your time zone to EDT and others.
Yes. And Victor yesterday sent out a reminder about this as well, but he may not have included the link for the tutorial. It'll be the same link as this one for the tutorial, which is 2 p.m. 2 p.m. Eastern Daylight Time. Okay, so today it's my pleasure to welcome our instructor, Kiri Stern, to tell us more about the fundamentals of image pre-processing, especially prior to deep learning model training. And again, as usual, land acknowledgement. If you do not know what land you're on, we encourage you to go to this link. Our virtual event is based in Montreal, Quebec, which is the traditional territory of the Kanakahaka and is on land which has long served as a site of meeting and exchange amongst indigenous peoples, including the Haudenosaunee and Anishinaabe nations. We acknowledge and thank the diverse indigenous peoples whose presence you can still hear me, yeah?
Yeah.
Okay, whose presence marks this territory on which peoples of the world now gather. We encourage you to learn and discuss about the history of the land on which you reside. And as usual, communications, we send out emails by medhacks2021@gmail.com, although currently our admin, Victor, has been sending some emails from his own account as well. So Victor Dumitru is our current executive administrator. Rules for participants, please do mute yourself during each presentations, and please don't use the whiteboard during the presentation and draw things on the whiteboard either. It'll distract the presenter. And then please use your real name and the same Zoom account every time. And if you have any more questions, please ask in the Zoom chat as well as the Discord channel. Our mentors and the organizers will be there to help. In terms of the timeline, this is an 8-week summer school workshop and seminar series. Currently, we're at week 2. Yesterday, we had our first seminar session of week 2 with 2 talks given by Dr. Julianne Cohen-Haddad and Dr. Marjorie Kohler. And today is the first seminar session of week 2, given by actually Julianne's student, Kiri Stern. Again, if you want to learn more about our timeline, please go to our website. And currently we're here on June 19th, Fundamentals of Image Preprocessing, Quality Assurance Prior to Deep Learning Training Model. And the next session will be the coming Saturday, which is on June 25th, which is the next seminar series. Seminar session. And again, Google Drive link will be available, and the unlisted YouTube playlist link will be available for you to look at after. That will be sending the conclusion and the next reminder email. And again, like Farhad has mentioned, and this is the program structure, we have the seminar workshop, and today in the afternoon will be our mentors tutorial session for last Friday's workshop that's been given by myself and Sebastian on the medical image processing fundamentals with CT and histopathology. And again, attendance, 70% of the workshop attendance and 50% of the seminar attendance will be counted. You can either attend or fill the quiz. Okay, now I'd like to introduce our mentors of today. Mikkel and Melinda, if you guys are in the audience, please feel free to unmute and introduce yourself. Are you guys in the audience? Mikkel?
Yep. Hello,
Hi.
everyone.
Hi.
Hi. Hi, this is Mikael. I'm one of the people helping out with the workshops. So nice to meet you all.
Yeah, would you like to introduce yourself a little bit? What are you doing? Where are you from? Yeah.
Yep. So I'm doing my master's in mechanical engineering. I am working with computer vision and spectroscopy to kind of predict some of the crop behaviors in agriculture. So pretty interesting work I'm doing. Yep.
Perfect.
I have a background in electrical engineering, but I do quite a bit of machine learning. So
Awesome.
it's useful in all fields.
Thank you. Welcome to the team. Melinda, are you here? I currently don't hear her. Okay, but it's okay that if she's not here right now, you guys will see her in the tutorial anyway, and she's going to create assignments and the quiz for you guys. All right. Okay, so now it's my pleasure to introduce the instructor of today, Kiri Stern. Kiri has a background in computational biology. She has had the opportunity to apply quantitative methods to varying biological fields such as microbiology, ecology, and genomics before discovering her interest in biomedical imaging. In her PhD, Kiri's research focuses on developing a federated learning strategy for continual learning and automatic segmentation of MS lesions in MRI of brain and spinal cord data. She is supervised by Dr. Julianne Cohen-Haddad with co-supervision by Dr. Sridhar Narayanan. Welcome, Kiri. Thank you very much for all your hard work. And please go ahead and start sharing your screen. Thank you.
Let me just share my screen. Can everybody see this?
Yes, thank you.
Okay, great. All right, so before we begin, if everyone could just make a copy of this notebook in their own drive, you can do that by going to File, Save Copy, as well as clear all outputs if you'd like to follow along that way. And then also please run the first line. Your copy is actually going to be a bit different from mine. I just got a receipt to receive what you guys are seeing, but the McMed Hacks team, they added these lines below to make it easier for you guys to download the data whereas I'm collecting it off of Kaggle, which is how most people will get it. So yeah, if you can, in your copy, if you can run the first line to download our data, as well as the next 3 lines here. And while you guys get that started, I'll just motivate again our presentation today and give an outline of what we'll be covering. So essentially, some of you may have already been familiar with different computer vision models, such as image segmentation or classification tasks. Now you want to apply it into medical images. And maybe for others, this is your first time being introduced to the whole topic of machine learning. But behind every high-performing model, it's really the data that it's been trained on. And this data needs to be pre-processed in a way that the model can learn relevant features for the task at hand. So in a sense, you could say that pre-processing is arguably one of the most important steps in your machine learning pipeline, because if you input garbage data, your model just won't learn anything. So today, what I want to cover is, first, we're going to go over the different types of medical imaging files that you may encounter. Then we're going to explore the data that we've been given, and then get into some ways of how we can pre-process this data. And finally, I'll show you some data augmentation tips that we can use to make our models more robust. Okay, is everything clear? Yes, it's good. Just to make sure that everyone has the data sets, you can find all of your download data if you go into the Files tab on the left-hand pane, and then in the Contents folder, you should be able to see all the download data. And I'll explain what we're going to be working with as we go along in the tutorial. So if everyone's good, we can begin. File formats. All right, so I think you guys should already have covered DICOM files. So I'm going to skip this section just for the sake of time and just get into the nifty file format, which is a format that the MRI neuroimaging community has adopted as sort of the preferred choice of files. And some reasons for this is that they can work with compressed nifty images, unlike in DICOM, where if you want to compress, it'll be at the pixel level. And also, we only need one single file per volume, whereas in DICOM, you would need a separate file for every single slice of your image. And for these reasons, we're just going to focus on nifty files today. Okay, so then, I included this BIDS in data structure because this is sort of a convention for how people organize their files. And if you're going to use like a pre-trained model that you find online, generally they'll require that your data is in this format. So that's just there for you guys to take a look at if you're interested. And now for this tutorial, we are going to be using the brain tumor segmentation dataset. And essentially every year since 2012, the BRATS challenge is released. And the goal is that teams will come up with the best tumor segmentation model. The I think it's on that. But the motivation behind this challenge is that instead of needing a radiologist to manually label hundreds of images, a model can do this task automatically. So the images we receive can, they'll depend on the MRI scanner's radio frequency pulses, or also known as the MRI sequence. And this will return a different contrasted image, as we see here. These are some examples, the T1 weighted, T2 weighted, and flare. And just to summarize, the T1 and T2 sequences are almost always used in MRI protocols because they do a really good job at capturing the appearance of tissues. And some obvious differences is that the white matter in the T1 weighted image will be very hyperintense or bright compared to the white matter in the T2 weighted. And conversely, the fluid in the T2 weighted is hyperintense. And this is really useful because when we deal with wanting to find like pathologies, the tissue will accumulate fluid as part of the immune inflammation process, and then this will make it easy for us to identify. So in my case, I'm looking at these lesions. And flare is just the same thing as T2, but it's fluid attenuated, so the fluid is in dark. Okay, so that's just a little summary of the data. And now to Oh yeah, okay, so now let's just get into working with this data. We're gonna take a single, so what we downloaded was a single T2 weighted image from the Bratz challenge. And we're going to use the Nibabel library to read this in. So if you guys can all import the necessary data, and then to load our file, we're going to specify the load function from the Nibabel package, and then the path to our file. And we're going to just assign this to an object called image, or img for short. And then, okay, so I'm actually going to skip some slides some cells that I have just for the sake of time, and you guys can keep it there as just like a reference. And I guess if you have any questions, please just put them in the chat, and hopefully the TAs can answer. But if they can't, then at the end I'll go over them, because just for the sake of time, I just want to make sure we can get through all the material since it's quite dense. So first thing we're going to look at is what shape are we dealing with? And we can do that by specifying our object, the image, and its shape. And here we can see that it's the 240 by 240 by 155 3D image. And when we're dealing with 3D images, we're actually working with a collection of voxels. And so if we think of a 2D picture, we know that a picture is made up of many pixels, each with their own value. So a voxel is just a 3D analog of this of a pixel. And the size of these voxels is really important for image quality. As you can see with this example of the cars, as we decrease our voxel size, we have an increase in the resolution of the object we're trying to observe. However, there is a trade-off between the signal to noise, or true signal and decreased spatial resolution. So this image right below gives a nice example of this. And we can see that as we increase the voxel size from 2 millimeters to 6, we have a better signal, but we also have, like, we're losing a bit of the resolution here, especially like you can see around the borders, and also there's more noise in this lower sampled space. Oh, and in case you guys didn't know, I've embedded a bunch of hyperlinks throughout the notebook. And if you're interested in learning more, you can just click on those hyperlinks and you'll get more information for whatever I'm talking about. And yeah, okay, so let's come back to our image at hand. Essentially, there are 3 parts to a Nifty file. It can be separated into the header with the metadata, the image data itself, and the affine matrix. So let's go through each of these. The header will contain the metadata, such as units of the measurement, the voxel size, etc. And we can call this by specifying our image.header and assign it to its own variable. And we can call this again. We can see its type. We see it's the Nifty1 header. And to get the voxel size, for example, we will specify the getZooms function. And in this case, we can see that it is a 1 by 1 by 1. Also, this means we can tell that it's the 1 millimeter isotropic, it's an isotropic resolution file. And isotropic just means that it's been sampled in the same, with the same length in all directions. So now we can look at the data itself. And we need to first fetch this data because it hasn't actually been loaded into our memory. And the reason for this is that it just saves space. If you're only interested in looking at like the metadata, you don't have to load all of the data into your computer. So to get the data, we need to first fetch it with the get like fdata or file data, and we're going to assign this to our image data object. And then it returns a NumPy memory map, but we can just treat this as a NumPy array. And so we can just, if we're interested, we can call the shape just like any other array object, and we see that it is the same as before, which is good. Now to look at the data, we can print it out by specifying the print function and our data. And here what we're seeing is a bunch of zeros. Why is this? Well, the notebook isn't going to print out every single value because that just wouldn't be useful for us. So it just shows the first and last couple number of arrays in each dimension. And they're all 0 because these part of the images just don't contain any signal from the brain. But we can index a patch of voxels in the middle of the brain to see or get an idea of what our data contains. And here, what we're doing is we're just specifying a 3 by 3 by 3 patch in the middle of the brain. And here's the output. We can see that the values that, well, what we're interested in is the relative values. So like, because it's a black and white image, essentially we can say that the greater the value, the higher the signal and the brighter the spot, kind of generally. So now we can take a look at our data. We'll index a slice, and essentially what we're doing here is we're saying at point 80 on the first axis, we're going to take all of the values in the Y and Z direction. So this, let me see if I can draw this out. It might be, I'm not sure how familiar you guys are with arrays, but if say we have our 3 axes for our data, we're basically saying at point 80, we want to take all of the values in the y-axis and all of the values in the z-axis. So then essentially we are left with this kind of image, and this is the image we're going to print. Is that clear? Okay, and if you change the index, they'll be basically selecting a different slice along your volume. So in our case, we're just choosing 80, just arbitrarily. How do I get rid of that? Okay, let's go. Great. So, so now let's print this out. We can plot it using matplotlib, as I'm pretty sure you guys covered already, and we see our image of the slice. Okay, so for the oh, is this good for everyone? Everyone is clear? I realize I'm just rambling on, but not really taking any pauses. I understand I realize the introduction is a bit long, but I just wanted to cover the basics so everything is clear for later. But essentially, now let's just go over the affine matrix. And okay, so right now our image is just sitting in some voxel coordinate space, ijk, but this isn't meaningful for us because we want to know what is this in our real world space, in our x, y, z coordinates. And the way we can transform the voxel coordinates into our real world coordinates is using the affine matrix. And the affine matrix allows us to do different scalings, such as translation or different transformations, sorry, such as translations, rotations, and scalings. And now I want to sketch a scenario in which the image's affine becomes important to give us a more clear idea. And let's say we are given a random nifty file. We'll use the same image as our brain, but pretend that we don't know what this file contains. So we want to plot out 3 slices, 1 from each axis. And we'll do so by first taking the middle coordinates or the center voxel. So we'll take the middle coordinates from each dimension. And here we can see that our center voxel will be 119, 119, and at point 119, 119, 77. And now, okay, yeah, you guys can please run the visualization functions, and you can go over those on your own time. They're just a nice way to see the data. So now we're going to plot the center coordinate using, we're going to first specify each slice, which is the ones we've just obtained here, the 119, 119, and 77, and we're going to plot it. So, so great, we've discovered this mystery file is actually of a brain. And what we also observe is that the first axis is the sagittal slice, which is going from left to right. The second dimension is of the coronal, which is from posterior anterior. And the last slice, or the last dimension, will be of our axial dimension. Yeah, so it's going from inferior to superior. And now, okay, so if I were to ask you, what side of the brain is our sagittal slice? Is it the left or right? If you guys think if it's the left, you guys can give like a little thumbs up. Or if you think it's the right, you can put a little heart. I'm trying to make this interactive for you guys. Or if you think you can't actually tell what side it is, you can put like the little check mark or something. Actually, I can't even see your reactions, I guess because I'm in sharing mode. But it turns out that due to the brain symmetry, we can't actually tell if this is the right or left side of the brain. And that's why we're going to use the affine matrix to tell us whether left in our voxel coordinate is also left in the real world. Okay. So in the real world, what we're saying is that everything is relative to the isocenter of the scanner, which will act as our 0, 0, 0 coordinate. And by convention, anything to the right, anterior, and superior of the isocenter should be positive. And we're going to use this RAS positive notation as a convention. So in order to transform our voxels into the real world coordinates, we simply need to multiply them by the dot product of our affine matrix and our coordinates. Okay, so let's get back to the interactive part. We can call our affine matrix using the dot affine of our image, and we'll store that as our object A for our matrix. And then simply we're going to, and this is just to see what point we're dealing with here. And to see what are our real life coordinates, we're going to multiply our affine matrix by our voxel coordinates. And as it turns out, we can see that our first coordinate lies to the left of the isocenter. It's 80, so these are in millimeters. Our second axis is, our second coordinate is 122 millimeters anterior to the isocenter, and our last coordinate is 77 millimeters superior to the isocenter. So we can confidently say from this that this slice represents the left side of the brain. Does this make sense? Right, I hope this is clear. But now, okay, now that we've covered what our images are and how we can look at them, let's move on to some image transformations. And it turns out there's this really good package called Torch.io, and this will allow us to do a lot of the like realignment and rotations that our affine matrix is designed to do, but here we can just call it with this package. So if you're following along by running the cells, could you just first run all the cells until the one that says print affine matrix and resample to standard MNI? And this is just because this one takes about a minute to run, so I just want to get that started beforehand if you guys are running this alongside. Okay, but we can come back to the top. So essentially, the data we're using for this section is coming directly from Torch.io. They have their own preset data sets. So here, what do we see off the bat? And I'm going to make this a little interactive, so you guys feel free to turn on your microphones if you want to comment on what we're observing. Okay, well, that's okay. I can explain it too.
It seems that the images are like rotated. I mean, you should in the upper part of the image, and in the lower part, they are just bad quality images, except for the one on the right.
Yes, exactly. Essentially, we're dealing with wrong orientation, as well as different voxels. The voxels are different, and we can see down below. Our top images are sampled at 1 millimeter isotropic resolution, whereas the bottom one, it has 0.75, 0.75, and 5.5. So those are the main things where we observe. We also can see that the top images are from a T1 weighted scan, and the second ones are from a T2 weighted. So we need to fix this, obviously. And one way to do this is by using the toCanonical function from Torch.io. And what this will do is it will switch all your images into the RAS convention. So this should have run. And now we see that our images are in the correct orientation, which is great. But we still need to place this in the same space as well as the same voxel dimensions. So what we'll do is we'll need to resample. And one way we can do this is by projecting all our images into a standardized space, which here we'll use the MNI space. And hopefully by now everyone's image has loaded. But if not, you can just look at my screen. And essentially here, if we print out what our object is, we can see that it's now all in the same sample space, as well as the voxel size are the same, which means we can manipulate our images properly. Okay, so this is just another structure that Torch.io uses. We don't have to go into it. It's just there for your reference. And over here, when we're using or when we're dealing with data from either a longitudinal study, so the same patient but over different points in time, or from different patients in the same study, we actually need to co-register the scans. And we're not going to go over this in this tutorial, but I left this here if you're interested. And there's a package called ANSPy, which will do this co-registration for you. All right, so now for some other techniques that are useful. The first one I want us to cover is the crop or pad. And the idea for this function is that sometimes we're only interested in a specific region. So for example, if we're working with like a thoracolumbar scan, but we're only interested in the spine, we can crop out all of the irrelevant parts of the image. And this will reduce the computational burden, as well as remove any external noise that may interfere with our model. So to demonstrate this function, we're just going to specify some dimension that we want to crop along, and then crop it with our crop or pad function from the Torch.io package. Excuse me. Okay, so when we print that out, we can see that we got rid of a lot of the background and kind of isolated the brain. But of course, whatever you guys are interested in, if you wanted to like crop in a different section, you can always specify that, depending on what your region of interest is. And yeah, again, for those who are following along, you would just need to run this cell here, because otherwise, when we get further along the tutorial, your RAM is going to exceed and it'll crash. So yeah, if you're following along, please run that. And okay, so another way we can reduce our computational burden is to downsample our images. And in this case, what we want to do is we're going to downsample our images to 3 times fewer voxels in each dimension. And as we can, so if you run that cell, as we can see, we've increased our voxel size from 1 millimeter isotropic to 3 millimeter isotropic. And as we've gone over, by increasing the voxel size, we've also decreased our image quality. But at the same time, we've decreased the amount of memory these images take. And in fact, this is by like 63 times less storage space. And this is just for one image. So you can imagine that when you're working with like a large data set, it can get really intensive when you have lots of images. So downsampling is just a nice way to reduce that burden on your computer. The problem, however, with downsampling is that it can cause the effect of aliasing. And here is this image will give a nice overview, or like a better view of what aliasing does. You can see these kind of streaks or artifacts in our image after downsampling. And so there are these methods to correct. However, and I added the code here, but it takes quite a while to run. So I'm just gonna skip that for now. But if you look at my screen, you can see the output. It's basically smoothed over, and it looks a lot better than if you were to downsample without this anti-aliasing property. Okay, is this okay so far? Yeah. All right, so now that we're happy with our pre-processing, let's move on to data augmentation. So some reasons for data augmentation is to, well, first overcome the possible issue of having a small data set. So we can apply image transformations like flipping the image or adding some rotation. And this is just a cheap way to increase the number of training samples without needing to go into back to the centers and getting more data or acquiring more scans. A second reason for data augmentation is that it'll help our model generalize. And well, generalize, so what I mean by that is that when you provide your model with images that it's never seen before, you want it to be able to still correctly get the features that we're interested in. So by adding certain augmentations to our image, which we'll go over, this will help your model learn these other possible features that it can encounter in the real world space. So some of the augmentation techniques are this random anisotropy. And what this function does is that it simulates the effect of downsampling our image and then resampling back to an isotropic space. And this is because not all images will be sampled isotropically, like we've seen with the T2 image, where we had the 0.75, 0.75, and 0.1 millimeter sampling. So then we can use this random anisotropic resampling function to simulate the different scenarios that we may encounter when working with other data sets. And here we can see an example of what this function does. We lose a lot of quality or information, but that's kind of the point, because when we want to increase the diversity of our data set to make essentially our model more generalizable. And the next function is the random affine. And this will just randomly transform our images with a certain scaling, rotation, or translation, as we've seen before. And to easily demonstrate what this function does, we're gonna load in a 2D image and then just apply a grid over it so that we can clearly see the changes. And so if you run this cell, we can see that it performs some sort of transformation to our original image. And because it's random, if you run it again, you'll get another transformation. So you can see the things that this function is doing. Okay, so there's also the random flip function, and flipping is a very cheap way to perform data augmentation. Essentially, you're just gonna flip along a certain axis, and this will already increase the amount of images you can have. So we do this by specifying the random flip function from our package. And we can specify what axis we want to flip over by using the keyword or argument axis. And here we'll specify inferior superior to flip along that axis, and then in this case, we can do the anterior posterior and we'll flip along to the second dimension. Okay. I hope I'm not going too fast, but I think you guys can all follow quite easily. Okay, so the next transformation that we'll look into is the random elastic deformation. And we use this function because we know that not all brains are identical. There's always some sort of variation in our anatomical structure from one individual to the next. So this is what the random elastic deformation function does. It will apply a nonlinear deformation to simulate these random variations between different patients. And okay, so here, to give another example, just a more example of what this function does, we can specify the number of control points for our image. And of course, 20 is way too much, but it's just to show what this function really does. And Torch.io will actually throw out this warning saying maximum displacement is larger, choose fewer control points or smaller maximum displacement. So if we take Torch.io's recommendation, let's just reduce the number of control points, increase the displacement. And here we can see a pretty reasonable or realistic transformation that would kind of implement like some variation between one person's brain from the next. Okay, so this is a pretty useful function in Torch.io. It's the one of, and essentially we can specify the proportion of images that we want to transform with either random affine or elastic deformation. And the reason for this is that random affine is just a lot quicker. So if we're short on time, or if you want to just optimize your time, you can specify that you want most of your images to be transformed with random affine compared to random elastic deformation. All right, so now that we've covered the spatial transformations, let's go over some intensity transformations. And the first one we can look at is the normalization. So we normally want to normalize images for the contrasts. And we want to do this in a way that preserves the relative intensities between values, but also allows us to have a common interpretation of tissues across samples. And so the first rescaling we can do is first change our scale to a smaller range. And we'll do this with the rescale intensity. And in this case, we're going to specify between -1 and 1. So this, as you can see, really narrows down the range that our values can take. But we also have some outliers with really high intensity. So what we want to do, to address this, we can specify percentiles. And here we're going to choose, we only want to keep the values between 1 and 99%. So anything outside of those will be forced to either -1 or 1. And here, okay, again, we can see with our histograms that even though we still have some really dark spots and a couple bright spots, our values are pretty much uniform, which is what we want. Excuse me. Another transformation is the SED normalization, where we're going to fit our values to a Gaussian distribution. And if we look, so when you run this and we get our histogram plots, when we look at our histogram, we can kind of see, well, it's kind of hard to tell, but we can kind of see a second mode over here. And this represents the foreground images. And since we're only interested in normalizing the values in our foreground, or basically, which is like our region of interest, we need to choose a certain threshold. So in our case, let's just try the mean and see if that's fine. And when we print it, it looks reasonable enough. we can see that the mask is clearly like separated our foreground from the background. So in this example, we're just gonna keep the mean as our threshold for normalizing. And to do this, I'll explain this a little bit more. Essentially, this is our function to normalize. This keyword argument is asking what's the mask we're going to use for our threshold, and lambda is a Python kind of unassigned function where we define it. So what we're saying here is that for every single value of x in our data, we only want to keep the values that are above all of the entire average or mean. So that's like, as we specified here, we're going to threshold everything above the mean value in our data. And so when we apply this, we can now see that our foreground is distributed above the 0, which is what we wanted. Was that good? Is that clear? It made sense. I think you guys worked with histograms already, so it should be a kind of a recap. Okay. So now for some data augmentation techniques. Let's start with, oh yeah, okay, well, as you said, data augmentation is just to help our model generalize. And we're going to start with the random blur. And okay, so random blur is kind of it's pretty similar to what we did with the random anisotropy. Sorry, that word threw me off. And when we apply it, we can see that the image has been blurred nicely. The next one we can do is add some noise to our data with our random noise function, and we can specify the standard deviation. And here we'll just choose 0.5 so we can really see what it's doing. Okay, so that is adding random noise to our data. And Torch.io actually specifies some MRI specific augmentations that really represent what we can get from MRI scanners. And the first one that we're going to look at is this random bias field. So the bias field is caused by low frequency signals, and these can corrupt our image as we see here. It's like darker compared to, there's like a bias here with the darker signal. And simulate this. Oh, okay, right. So there's also, again, another Python package called AntPy that will correct for this using the different algorithms. But if we're just interested in augmenting our data to imitate this, we can use that with the random bias field function. And here, when we print out our image, we can see, or when we apply the function to the image, we can see that it has applied this kind of artifact that will, imitate what the random bias field that can happen in actual scanners. Okay, so case space, there are other so the case space is basically, sometimes when the space is altered, it'll create different artifacts. And here I'm just showing the random spike, which is just like these streaks that can happen in the images that you can obtain. There's the random ghosting, where it's kind of, you see these little ghost images. So this function will try to imitate that, as well as random motion. And this function will provide, like, kind of imitate that motion that could happen in our scanners. And for these functions, I actually don't I couldn't find a Python package that would correct for them. But personally, I haven't actually received any or had to work with data that had any of these artifacts. So yeah, I guess if people, I guess there are ways to correct for them because there are algorithms that have been proposed, but I just don't know of any Python package that will do that for us. Maybe one of you guys have experienced it and know. And again, to reiterate, it can sound counterintuitive to like blur our data or add random noise or perform any other transformation. But again, this is done because we want to improve our model's ability to generalize. And this will just make it more robust when it's applied to data that it's never seen before. Okay, so some tips and tricks. There's the compose function in Torch.io, which just allows us to wrap all of our functions that we want to apply and then apply them in sequential order. So you really need to make sure that you're aware of what transformations you're doing, because for example, if you add random noise and then you blur, you're going to remove all of the blurring you just did, all of the random noise you just applied. So the order is important. Some tips to go faster: you can use the nearest neighbor when interpolating the random noise, the random motion, sorry. The interpolation, I think if you notice back when we were doing random noise, I don't want to scroll back up, or I can. But essentially it was one of the keyword arguments, and then we specified the nearest neighbor. Well, anyways, you guys can see that. And also in the documentation. So if you guys probably noticed, I've linked all of the documentation for each function, and you guys can look at that as well. So other ways is that, as we discussed, we can crop our images, as well as downsampling. And then we also have the one of function, which specified the proportion of either random affine or random elastic deformation. And random affine is faster, so you can put more weight or more probability of your images being transformed by random affine. And then also, Torch.io allows us to see the history of what transformations we've done. So if we take our downsampled image and we look at its history, we can see that we've resampled it, we've cropped it, and we've resampled to, I guess resampling is also is downsampling here. Yeah, so that's just a good way to keep track of what exactly we've been doing to our images. And oh yeah, when it comes time to testing, we don't need to add any augmentation techniques to our testing images, because like we're essentially introducing new photos to our model. And we want to see how our model performs on the data that's never seen before. I guess I'm ahead of time, which is good because we have about 15 minutes left for questions after. But to conclude, basically what we've covered is we saw how we can get our data, how we can look at our data, and then also went over the Torch.io pre-processing functions to get our data into the same space, as well as the augmentation technique. And below, this is for you guys if you want to try out all the functions that we've covered today. I got an image from the Visible Human project, which is from below, and then here's a pipeline you guys can follow just to test out everything that we've covered. And then you can run your own code here, and I've included the solutions below if you want to check it. So that's it. Thanks. I guess. yeah, I guess that is it for me.
Thank you so much. I think at this point we can open up to Q&A. If there is any question, feel free to raise your hand through the Zoom and we will ask you to unmute and ask your question. Or if you prefer, feel free to just write your question on the chat and Eugene will go through it.
Yeah, great. So does anyone have any questions or, oh, great. Hussein, go ahead.
Hi, so thank you so much for the great overview of all the transformations. I have a question about the histogram part when you applied the foreground, when you separated the foreground from the background. It seems like after applying the filter, so can you scroll up?
Yeah,
Just to the histogram, yeah, thanks. Yeah, that's it. So maybe scroll a little bit.
Is that normalization for here?
Yeah.
Yeah.
Right. So can you scroll down a little bit? Like I just want to pick the picture of the histogram before and after. Yeah, that's it. So yeah, so it seems like the histogram got shifted. So like I thought originally that you're gonna remove all of the voxels after, like if they're like bigger than the mean, we're gonna keep them. If they're smaller than the mean, we're gonna like remove them or something. But like what I see in the histogram is that like the voxels that are less than 0, so like when the shift happens, we have like, what is the x-axis? Like what is the, yeah, exactly. What is the x-axis? Like what does -2 mean here?
So here, okay, that's a good question. Essentially, when we're normalizing our data, we're subtracting, we're dividing by the mean and subtracting by the standard deviation. So at first, we're going to do that for all of our data, like as to see what this function does. We do that across all of the data, but because we're only interested in the foreground or the pixels in the foreground, because we want to separate the background from the regions of interest, we want to take our second mode, which is what's going to separate the background to foreground. Here, maybe there's I wrote in the document here. This is a good link that kind of illustrates what's happening with a better. So scattered throughout the documentation, there's a, oh, maybe it doesn't have this, but I think maybe you guys covered. Have you seen histograms before in a different tutorial?
Yeah.
Yeah, okay, so you know that when you want to separate between the background and the foreground, I think in your case, you might have had a more clear separation between the values. But essentially, what we're doing is we're then only applying our normalization across the values above what our threshold, which we in this case selected as the mean.
Okay. Yeah. Makes sense.
So
yeah, like when we subtract from the mean, then every like value that is smaller than the mean will have like a negative number, right? And then yeah, but I'm just like curious of like how like the negative number is shown in the pictures, if that makes sense. Because like,
well, you can have negative numbers when you normalize, right? Because you're
sure, but like so correct me if I'm wrong, but like what I understand from the histogram on the bottom is that some like the number of pixels or voxels with value of -1 are, for example, like it's like 25% of the voxels have like value of -1. Does that make sense? What I'm saying?
Oh, okay. So yeah, so this is I think maybe it's a bit confusing because I put it right after the rescaling. But when in this case, like this was the first transformation that I was showing with when we rescale the image, but when we're applying the normalization, it's not on the non-rescaled image. We're just using the original one.
Right. Okay.
I also can add something here. This is common usually for medical imaging. You have background area. For example, for a CT image, you have air, which is the Huntsville unit for it is around -1,000. So the background area is high frequency, of course, because you get the same, almost the same, intensity value for those background area. This is why you see a peak. And in general, normalization is a step that most often we'll hear more about deep learning starting next session, but it is a good practice for normalizing your data before feeding them to the model. It has a good, down the road, you'll find out why normalization is valuable. I don't want to go ahead at this point, but this is the essential step for any pipeline that you do. Normalizing data make your pipeline more stable and make it way easier to train your model. And you do it by subtracting mean and division by standard deviation. So it's really computationally fast. It's not a computationally intensive operation, but it is really valuable for improving the performance of the model.
Right. Thanks. Yeah.
All right, great. Thanks, Hossein, for your question. Thank you for your further explanation, and thank you, Kiri, as well. I see a few more questions. So, a question that's been asked by Johnny during the presentation was: is there a way of looking at the complete volumes? I tried once with a for loop iterating over one dimension, but the figure does not update. And then Farhad answered that you can use 3D Slicer. Yeah, 3D Slicer is very useful for visualizing a 3D volume. But I guess, Johnny, you're asking how to do that with how to visualize the entire volume by iterating it in your code. I guess that's what you're asking. You can unmute and feel free to ask it yourself as well.
Yes, that's what I meant.
Okay.
If there's a way of doing that in Python. I tried like putting a wait that 1 second or something like that for it to actually like update, but it didn't update. So I'm not sure if you guys know about any way of actually seeing volumes on Python.
Oh, I understand. So like the whole, like seeing, okay. So like if we take a GUI, for example, like FSLIs, and you want to like, if you move your cursor,
Like
it'll
like a slider or something.
yeah. Oh, I see.
Just exploratory, you know,
Oh,
something that goes from top to bottom, just to see that there's nothing weird.
well, were you able to print out at least a 2D image of that whole volume?
Like printing all the 2D images automatically.
You
So
are
start
able
with
to.
the top one and go to the up until the bottom one.
Oh, you just want to print all of them. I think Kiri, you have a really like where you visualize just one line, and then I think it was you visualize a 2D slice of the entire volume, 80 comma yeah this one, and then you can probably just iterate through the entire volume like this, where you change 80 into an index. Well, yeah, sorry, keep going. Kiri, go ahead.
No, that's exactly. It didn't work. Like you can just write a for loop essentially, and from the length of the range length of your whole object in this dimension, and print out through all of those indices.
Does that answer your question, Johnny?
Yeah.
But
I mean, I'm not sure if that was like a problem at that time, but I mean, I tried that. I tried doing a for, but the image doesn't like update. It either shows like the first cut or the last cut. I don't remember.
Might have been an indexing issue then, I feel like.
Okay, I'll take a look. Thanks.
Yeah.
Also,
but also,
yeah, go ahead.
Oh no, go ahead. No, I was gonna say just when, like for me, because we have so many images, what we usually use are these graphical user interfaces, the GUIs, and I use Fossilize, and essentially all you need to do is drag and drop your images, and then it'll have what you're essentially going after is looking for the 3 places, and then you can like just move your cursor and it'll show all of the slices in different dimensions. And that's a really good way to quickly visualize what your data is using. But because this is a Python course, we're showing how to do it by indexing through each slice. But Farad, you have to say.
Yeah, I think if I understand the issue, the reason that you didn't get an update is that for Matplotlib, in order to get the update for the canvas and the figure, you should need to call plot.show. So plt.show. So that might be the case, but as Kiri suggested, the best way to really visualize the volume is through GUIs. However, this doesn't mean that processing your data and visualizing it through the pipeline can be completely done by those software. No, those software is an easy way to go through the volume like 3D Slicer, for example. However, sometimes when you design your pipeline, you want to see that, for example, if you compose a pipeline of the data augmentation, you want to see what is the output. For those cases, it is a good idea. But in general, if you want to have something that's like a widget, it is a little bit challenging to control it, and it's limited in use cases also. So, but if you want to show it and do it one by one through Matplotlib, you need to do plt.show. That's really update the current canvas and show the figure. And you can close that one and go to the next one.
Yeah, I think another really useful library, visualization library is called Bokeh, like Bokeh, and it can, if you want to have a slider of all of the slices in your volume, you can slide that as well. You can code that in as well. It's also a good exploratory tool. But like Farhad said, the GUIs are a good idea, definitely to get it for stealing. Okay, next question by Gaganpreet. If you're here, you can unmute and ask yourself as well. But his question is how to align the para-axial images of MRI into true axial images with affine operations.
Sorry, can you repeat that? How to
align the para-axial images of MRI into true axial images with affine operations.
Like if we were not.
Is there any transformation to align the contours on para-axial slices to true axial axis?
Hello, yeah, can you hear me?
Yep.
Yeah, I am asking about like in some of the MRI images, they are not true axial images. They are having some angle with the true axial planes. So how to correct those angle to align MRI images into the true axial images? So my question regarding that, like in a gamma knife, the physician used to contour the MRI images over the paraaxial planes, and the contour is also drawn on the paraaxial images. But I want to import those paraaxial images into the TPS. That will only import the true axial images. So how to convert those paraaxial images into the true axial images, so that I can easily import into the TPS?
Oh, is it so you're saying the slices that you've received are not like a flush kind of on your axial axis?
Yeah.
Okay, so there is actually here, if you go into the documentation for the NIPA bell, they show how the different scale, or like here, they give you like information on how images are rotated and scaled, like with the different transformations. So I guess if you know how far off your
that is given in the DICOM tags, like image orientation patient IOP tag of the DICOM images. So usually it is 100010, the image orientation tag in DICOM files. So in para-axial images, there is some angle given. Instead of 100, it has some value like 0.06 or 0.07, something like that. In that case, how to convert those images to the true axial images? That information, the angle around the x-axis, y-axis, and z-axis is given in the DICOM format. In DICOM tag, that is image orientation patient tag inside the DICOM file.
If you, I can
Okay.
add, yeah. Go ahead.
Yeah, maybe you'd be more adept at answering this because I've actually never worked with DICOM files.
No
We always
worries.
use
Yeah,
Nifty.
this happens as you actually the screen that you have shared. It's a good way to answer this question. Usually, when you have this information, you can find out the degree that you need to change. So you get this information from the DICOM metadata, and when you have that, you convert and find the degree of rotation. When you have the degree of rotation, through the rotation operator that's here suggested, you can rotate image back. So if it is, let's say, 10 degree across this axis, you make it minus 10 degree across that axis to come and align to the axial axis or standard way that you want to show the data.
So is there any example in these notebooks, something like that? Because I was unable to perform that operation on the images, multiple images.
I
No,
haven't
I don't
seen
have that.
any. Yeah, I haven't seen any too. So it requires a little bit of reverse engineering, but you have the data. From that data, you calculate the metadata, you calculate the degrees of rotation. And when you have the degrees of rotation, you negate them and call that rotation 3D image rotation function.
I did that, but the next difficulty is the same problem comes when I try to align the contours, which was delineated on the para-axial images. So the same problem comes when I want to align those contour on the axial images. So in that case, it quite become little complicated problem.
Yeah. So regarding the contour, you shouldn't, do the same degrees of rotation, or let's say reverse rotation. However, one thing which is really important for contours is that when you do the contour and do these operations such as rotation, you need to use nearest neighbor with as interpolation method. Otherwise, your contour won't be consistent, and you might have values that doesn't make sense based on the let's say contour values in the contours, because sometimes we have in the contour file, we have, let's say if we have just two or three organs, we have usually use integer numbers 1, 2 or 3, but interpolation introduce new values, and we don't want to see that. Because of that, you need to do nearest neighbor. But any update that you do on the image, you should apply the same update on the same transformation on the contours as well.
So one more question regarding when I do such kind of operation on these two matrices, like one is the image matrix and another one is the contour matrix. So it also changes the voxel size of those two matrices. So how can I interpolate over those voxels throughout the matrix?
So my suggestion is that first make your images isotropic and then apply the transformation. So in that case, and at the end of the day, you always can go back to the resolution that you want. However, during this process, depends on the function that you use for interpolation. You might get a little bit of change. Linear transformations, interpolation is fast. However, other interpolation might be a little bit slower, but more accurate. Okay. So isotropic transformation, it's the first things that I usually suggest to apply to bring everything to the isotropic space, and then apply the rest of the transformations.
Okay, thank you.
Great. Thank you for your question, Gaganpreet. Next question that we have is from Mohammed. If we use each slices of a 3D separately like 2D images, what will be the effect? Because training a model for 3D images need much more GPU memory. If we use each slices like 2D, what would be the effects? Do you understand the question?
Yeah, I think,
yeah.
well, like when we separate them into 3 different the slices, it's just to visualize. But when we actually feed into the model is the full volume. So we're not feeding in like a bunch of 2D slices from every single axis. We're giving the model a full volume. And like there are a bunch of different models that you can look at. Like what, for example, you'd have to find a 3D like a model that would be able to take in these volumes. So like there's a modified 3D UNet, which is a segmentation model that receives in the 3D volume of your structure.
Also, another reason that, as Kiri suggested, we most often it's the best approach to have feed the whole volume to the model. But the problem is that sometimes you look at a specific area in the image, and most of the 2D slices do not cover that area. So that's the challenge. For those cases, if you use 2D, it might be most of, if you feed 2D to your 2D images to your model, most of the images that you feed to the model does not contain that organ. That's a challenge. Plus, you need to come up with a way to combine the output of model per these, let's say, slices, and then come up with one prediction for the whole model. So that's another challenge. And if you want to do a 2D analysis, so it's not impossible, but it's better to see the whole image, because to make that process theoretically easier. However, I understand that for GPU is a bottleneck. This is why, as Kiri suggested, you use this transformation to perhaps downsize the image, or more specifically, the better ways to really crop the area of interest for the image. In that case, you substantially decrease the volume size and make it easier for the model to be trained with a larger batch size. For 3D images, most often, if you feed the whole 3D image to the model, it is your most GPUs do not support that kind of for large model, that they don't have enough memory to support that kind. So you need to get creative. Most often use a patch-based approach to handle those cases.
Then would you like to elaborate more on sort of the advantages of 3D over 2D, or the pros and cons of both?
So is this question for me?
Yes.
Yeah, sure. So 2D, obviously, the nice thing about 2D is that you can train larger model with available, even with small CPUs. By larger model, I mean, so your input will be used, and most often you need to have a batch size of it. So this means that, let's say, a batch size of 32. For 2D means that, really, this means that 32 a slice. But for 3D, this means that if you have a CT image, for example, with 300 a slice, a batch size of, let's say, 32 means that a batch size, if you have 32 images, 32 times 300. So this is, for most GPUs, impractical. The problem is not just the input size. The problem is that the model needs to keep track of all of the calculation across the layers. So that's a lot of computation, and most models crash for those. So what alternative is to decrease the batch size, or use techniques to calculate these terminology that I use. It's for perhaps things that you will hear about it in the future sessions. But to keep track of all of this computation and calculate the you know, gradient for the model for different parameters, it is a really challenging to do it. Some of the operator, as I mentioned, there are techniques to, you know, bypass some of this. For example, you can do the back propagation once in a while, but this is not the best for some of the operations, like normalization approach that use a batch size. So in general, there are those challenges that we need to face. But the nice thing about 2D is that if it's possible, if you have 10 samples, this means that 10 times, and each sample is around 200 slices. Number of slices that you can use is 300 times more than number of samples. The downside of it is that most often you are interested in a specific area of, let's say, for head and neck or for brain imaging, a specific area of the brain. So this means that most of your images, they are really irrelevant and there is no contour associated, or the contours are empty for them. So that's the downside of 2D. And I once again, when you want to make a prediction for one patient, if you do it in 2D, 2D analysis, you have, let's say we have 300 slices, you have 300 predictions. You need to combine these. There are ways to combine sequence of information, but those are extra work and extra complexity for the model. If it's possible and we can do a 3D analysis, 3D analysis is perhaps the most straightforward. I mean, the challenge, and the only challenge, honestly, is two challenges. One, computationally and having a GPU that can support that. And the second is that number of samples. If you don't have these issues, or you can solve these two issues by using patch-based, you are better off to go with 3D models. Perhaps another reason for 3D model is that not only they see one slice, they see the area around that, and that's also important for making prediction. You're just looking at a small area and one slice, you might not really be able to, even expert might not be able to predict and diagnose that issue or that specific phenomenon there. So those are some pros and cons of 2D versus 3D. Is there anything else you want to add here?
I think you.
Perfect. And then I think we have another question from Johnny. What are the pros and cons of Torch.io compared with AntsPy or similar libraries? I've actually never heard of AntsPy before. So please go ahead.
Yeah. So actually, it's kind of funny to say, but so the pre-processing pipelines that I use aren't actually this, because we have in our lab we have our own module that we use. It's called the SCT toolbox for pre-processing. So yeah, I don't actually have any experience with with these, and for the tutorial, I had to look all of this up for you guys. But yeah, for AntsPy, I think this was really what I was told is like for co-registration, it allows you to do the rigid registration, which is essentially when you're just overlaying your same patient and you just want to like put them in, like rotate them into the same plane. But for elastic, which you need for different patients, it will do a non-linear transformation to put them into the same space. And if you're more interested, there are here like the links that I've included, so you can read more about it, and like AntsPy here, the documentation for the different registrations. I'm sorry, I don't have a better answer for you.
I can also say that I haven't been working with AntsPy. I guess AntsPy is based on a Python version of Ants, and Ants is used to be a common approach or common really library for image registration. For those of you who might not be familiar with image registration, sometimes we have several images for one patient, as you can guess, during this imaging, people move, and not only people move, sometimes because of a different area of the body, for example, for hearts. So there you never get the images that are still and the same. So you need to adjust them, and there are different, let's say, registration images to align these. The purpose of registration is to align these images. Registration usually tries to, it's good for, sometimes it's good for brain imaging, but for many areas it's not working. For example, for abdominal imaging, because of the movement of the actually the heart, as well as different body volumes in abdominal. Depends on how much you eat. All of the organs will be shifting around. So there are packages there for Torch IO. One nice thing about these packages, it has been designed in a way that it is really the terminology, the function, the way that you use it is consistent with the other parts of the Torch. And for those of you who have been using Torch for machine learning, for natural images, like images of cat and dog, you feel and see all of the similar functions, like that works almost in the same way, regardless of the modality of the data. So that's a nice point about the Torch IO. The other things that I would say is that these packages they have a large user base. Because of this, they are well maintained. There are many people that contribute to these, and they more specifically for Torch environment. This new updates will come up, new transformation will show up, and you learn something that's grow. For Ants and AntSpy, as I mentioned, I haven't been using it. AntSpy, definitely. I'm not sure how active those are, but there are functionalities that one package offer, and it's absent in the other packages. So don't sign up for a specific package and say, no, this is the best. Always see all of the options that you have and check for this application that you have, which one is the best. That's my suggestion.
Thank you so much, Farhad and Kiri, for both of your answers. And I think we're right on time if we don't have any more questions. Thank you so much for coming today. It's at noon. And the next session that we'll have will be this coming Saturday. We'll hear 2 talks from Dr. Caroline Reinl and Dr. Ann Appold. So it will be a very exciting session. We really look forward to seeing you guys in a week on June 25th. Thank you very much. Have a great week.
Thank you.
Oh yes, there's a tutorial today at 2 p.m. Please sign in with the same link as this one.
Okay, thank you.